The inverse trig functions. Let's begin with a review of how the inverse sine function is defined. We begin with the graph of y equals sine x, whose domain consists of all real numbers x. This function has no inverse since it's not one-to-one. That is, it's not true that each y in the range is the value at exactly 1x. In other words, the graph fails the horizontal line test, so if we reflect the graph about the line y equals x, the resulting graph will fail the vertical line test and therefore not be the graph of a function. So we restrict the domain in such a way that the function will be one-to-one. The standard way of doing this is to restrict the domain to the interval from minus pi over 2 to pi over 2. Now let's blow up that part of the picture, draw the line y equals x, and then reflect the graph about that line. This is the graph of the inverse sine function. Its domain is the closed interval from minus 1 to 1, and its range is the closed interval from minus pi over 2 to pi over 2. All this comes down to the following definition. The equation inverse sine of x equals y is equivalent to sine y equals x, and y is between minus pi over 2 and pi over 2. In other words, inverse sine of x is the number between minus pi over 2 and pi over 2 whose sine equals x. Now let's recall the standard exact values of the sine function for first quadrant angles. The sine of 0 is 0, the sine of pi over 6 is 1/2, and so on. If we reverse these pairs, we have a table of values of inverse sine. Inverse sine of 0 is 0. Inverse sine of 1/2 is pi over 6. Inverse sine of root 2 over 2, or 1 over root 2, equals pi over 4. Inverse sine of root 3 over 2 is pi over 3. Inverse sine of 1 is pi over 2. Also, inverse sine is an odd function, just as sine is. Inverse sine of minus x equals minus inverse sine of x. So from the table there, we have inverse sine of minus 1/2 equals minus pi over 6, and so on. The derivative of inverse sine of x. We start with the equation sine of inverse sine of x equals x. Then we differentiate each side with respect to x. This gives a 1 on the right-hand side. On the left side, we use the chain rule and get cosine of inverse sine of x times the derivative of the inside function, which is inverse sine of x. Now we divide by cosine of inverse sine of x to obtain the derivative of inverse sine of x equals 1 over the cosine of inverse sine of x. Now let's simplify. For this, a diagram of a right triangle is a helpful device. Label one of the acute angles as inverse sine of x. The sine of that angle is x, so we can label the opposite side x and the hypotenuse 1. That makes the adjacent side have length equal to the square root of 1 minus x squared. Thus the cosine of the angle is the square root of 1 minus x squared divided by 1, and so the derivative of inverse sine of x equals 1 over the square root of 1 minus x squared. Let's think about this in terms of the graph of inverse sine of x. Here's the graph of its derivative, 1 over the square root of 1 minus x squared. Notice that the derivative approaches infinity as x approaches 1 from the left and as x approaches minus 1 from the right, and it has its minimum value at x equals 0, where the graph of inverse sine has an inflection point. The inverse cosine function. We begin with the graph of y equals cosine x, whose domain consists of all real numbers x. Just as with the sine function, cosine has no inverse since it's not one-to-one. So we restrict the domain in such a way that the function will be one-to-one. The standard way of doing that is to restrict the domain to the interval 0 to pi. So let's blow up that part of the picture and draw the line y equals x, and then reflect the graph about that line. This is the graph of the inverse cosine function. Its domain is the closed interval from minus 1 to 1, and its range is the closed interval 0 to pi. All of this comes down to the following definition. The equation inverse cosine x equals y is equivalent to cosine y equals x, and y is between 0 and pi. In other words, inverse cosine of x is the number between 0 and pi whose cosine equals x. Now let's recall the standard exact values of the cosine function for first and second quadrant angles. Cosine of 0 is 1, cosine of pi over 6 is root 3 over 2, and so forth. Now if we reverse these pairs, we have a table of values of inverse cosine. Derivative of inverse cosine of x. Here we'll use an identity to write inverse cosine in terms of inverse sine. The inverse cosine of x plus the inverse sine of x equals pi over 2. This is basically about the fact that when x is between 0 and 1, inverse cosine of x and inverse sine of x are radian measures of complementary angles as shown here in the figure. So inverse cosine of x equals pi over 2 minus inverse sine of x. This means that the graph of inverse cosine may be obtained from the graph of inverse sine by first reflecting it about the x-axis to obtain the graph of minus inverse sine, and then shifting that upward a distance of pi over 2. Now let's differentiate both sides of the identity, and we find that the derivative of inverse cosine of x is the negative of the derivative of the inverse sine of x, and so we have minus 1 over the square root of 1 minus x squared. Now here's the graph of the derivative. Notice how that corresponds to the shape of the graph of inverse cosine, thing new. The inverse tangent function. We begin with a graph of y equals tangent x, whose domain consists of all real numbers x that are not odd multiples of pi over 2, that is, all x where cosine x is not 0. This function has no inverse since it's not 1 to 1, so we restrict the domain in such a way that the function will be 1 to 1. The standard way of doing that is to restrict the domain to the interval between the two vertical asymptotes closest to 0. Those are y equals plus and minus pi over 2. So our restricted domain is the open interval from minus pi over 2 to pi over 2. So let's draw the line y equals x, and then reflect the graph about that line. This gives us the graph of the inverse tangent function. Notice that the vertical asymptotes to the graph of tangent have reflected to become horizontal asymptotes to the graph of inverse tangent. The domain of inverse tangent is all x, and its range is the open interval from minus pi over 2 to pi over 2. Notice that since the values of tangent at plus and minus pi over 4 are plus and minus 1, the values of inverse tangent at plus and minus 1 are plus and minus pi over 4. Also, inverse tangent of x approaches pi over 2 as x approaches infinity, and minus pi over 2 as x approaches minus infinity. All this comes down to the following definition. The equation inverse tangent x equals y is equivalent to tangent y equals x, and y is between minus pi over 2 and pi over 2. In other words, inverse tangent of x is the number between minus pi over 2 and pi over 2 whose tangent is x. Now let's recall the standard exact values of the tangent function for first quadrant angles. Tangent of 0 is 0, tangent of pi over 6 is 1 over root 3, tangent of pi over 4 is 1, tangent pi over 3 is root 3, and the limit as x approaches pi over 2 of tangent x equals plus infinity. If we reverse these pairs, we have a table of values of inverse tangent. So inverse tangent of 0 is 0, inverse tangent of 1 over root 3 is pi over 6, and so on. Also, inverse tangent is an odd function, just as tangent is. Inverse tangent of minus x equals minus inverse tangent of x. So from the table there, we have inverse tangent of minus 1 over the square root of 3 equals minus pi over 6, and so on. The derivative of inverse tangent of x. We start with the equation tangent of inverse tangent of x equals x, and we differentiate each side with respect to x. This gives 1 on the right-hand side. On the left side, we use the chain rule, recalling that the derivative of tangent x is secant squared x. So we get secant squared of inverse tangent of x times the derivative of inverse tangent of x by the chain rule. Now secant squared is 1 over cosine squared, so let's multiply both sides by cosine squared of inverse tangent x. So that's the derivative of inverse tangent x. Now let's simplify. Again, we'll use a right triangle for help. We'll label one of the acute angles as inverse tangent of x. Then the tangent of that angle is x, so we can label the opposite side x and the adjacent side 1. That makes the hypotenuse have length square root of 1 plus x squared. Thus the cosine of that angle is 1 over the square root of 1 plus x squared. Squaring that gives us 1 over 1 plus x squared as the derivative of inverse tangent x. Now let's think about this in terms of the graph of inverse tangent x. Here's the graph of its derivative, 1 over 1 plus x squared. Notice that the derivative is always positive, corresponding to the fact that inverse tangent of x is always increasing. The derivative approaches 0 as x approaches plus or minus infinity, corresponding to the fact that the inverse tangent graph approaches horizontal asymptotes as x goes to plus or minus infinity. And the derivative has the maximum value at x equals 0, where the graph of inverse tangent has an inflection point. The inverse secant function. We begin with the graph of y equals secant x, whose domain consists of all real numbers x that are not odd multiples of pi over 2, that is, all x where cosine of x is not 0. Again, this is a function with no inverse since it's not 1 to 1. So we restrict the domain in such a way that the function will be 1 to 1, and one way of doing this is to exclude from the domain all numbers outside the interval 0 to pi, leaving only one vertical asymptote at pi over 2. So our restricted domain consists of all x in the closed interval 0 pi except pi over 2. Now let's draw the line y equals x, and then reflect the vertical asymptote at x equals pi over 2 to obtain a horizontal asymptote at y equals pi over 2, and then reflect the graph. This is the graph of the inverse secant function, with domain consisting of all x outside the open interval minus 1 to 1, and range consisting of all y in the closed interval from 0 to pi, except pi over 2. We will skip the details here for brevity, but it turns out that the derivative of inverse secant of x is equal to 1 over the absolute value of x times the square root of x squared minus 1. Notice that this is undefined when x is in the open interval minus 1 to 1, as it should be, because the inverse secant function is undefined there as well. Now we have only to consider inverse cotangent and inverse cosecant. Just as in the case of inverse sine and inverse cosine, we can think of inverse tangent and inverse cotangent as complementary angles. That is, they always sum to pi over 2. Thus, their derivatives are negatives of each other. So the derivative of inverse cotangent of x is minus the derivative of inverse tangent of x, or minus 1 over 1 plus x squared. Likewise, inverse cosecant of x plus inverse secant of x equals pi over 2. And so the derivative of inverse cosecant of x is equal to minus 1 over the absolute value of x times the square root of x squared minus 1. Now let's make a table showing derivative formulas for all 6 inverse trig functions before doing a few example computations. The derivative of inverse sine of x equals 1 over the square root of 1 minus x squared. The derivative of inverse tangent of x equals 1 over 1 plus x squared. And the derivative of inverse secant of x is 1 over absolute value of x times the square root of x squared minus 1. Derivatives of the corresponding inverse cofunctions are all negatives of these 3. Examples. Let's find the derivative with respect to x of 1 minus x squared times inverse sine of x. We need to use the product rule here. We'll first take the derivative of the first factor, 1 minus x squared, that's minus 2x. Multiply that by inverse sine of x, and then add 1 minus x squared times the derivative of inverse sine of x, which is 1 over the square root of 1 minus x squared. The quantity 1 minus x squared is the square of the square root of 1 minus x squared, and so we can do a cancellation and write our second term as the square root of 1 minus x squared. Now let's take the derivative of the inverse tangent of x over 2. The outside function there is inverse tangent, the inside function is 1/2 x, so the chain rule tells us to put x over 2 into the derivative of inverse tangent. So we have 1 over 1 plus x over 2 squared times the derivative of x over 2, which is just 1/2. Now let's notice we have an x squared divided by 4 in the denominator, so let's multiply the top and bottom of this fraction by 4 to obtain 2 over 4 plus x squared. Now let's take the derivative of the inverse secant of the square root of x. The outside function is the inverse secant, so we substitute square root of x into the derivative of inverse secant, which gives us 1 over the absolute value of the square root of x, which is just the square root of x, times the square root of the square of the square root of x minus 1. So now we need to multiply by the derivative of the inside function, square root of x. That's 1 over 2 times the square root of x. Now we multiply denominators. There's a square root of x times the square root of x for an x, and so we have 1 over 2x times the square root of x minus 1. A few more examples. Let's take the derivative with respect to x of inverse cosine of e to the minus x. Now let's recall that the derivative of inverse cosine x is minus 1 over the square root of 1 minus x squared. So we use the chain rule here. We substitute e to the minus x into the derivative of inverse cosine of x. Note that the square of e to the minus x is e to the minus 2x. Now we multiply by the derivative of the inside function e to the minus x, which is e to the minus x times minus 1. And so now we simplify here, and we have e to the minus x over the square root of 1 minus e to the minus 2x. Let's take the derivative of the inverse tangent of the square root of x. First recall that the derivative of inverse tangent of x is 1 over 1 plus x squared. So we substitute square root of x into that derivative, and then multiply by the derivative of the square root of x. So we have 1 over 2 times the square root of x times 1 plus x. Let's find the derivative of the inverse tangent of x divided by 1 plus x. Here again we use the chain rule. We have 1 over 1 plus the square of x over 1 plus x, or 1 over 1 plus x squared divided by the square of 1 plus x. Now we multiply by the derivative of the inside function, which we'll do with the quotient rule. We'll have something divided by the square of 1 plus x. The numerator will be the derivative of x, which is 1 times 1 plus x, minus the derivative of 1 plus x, which is also 1 times x. So the numerator here is 1. When we multiply out the denominator, we have 1 over the square of 1 plus x squared. And let's notice that this expression is defined at minus 1, even though the original function is not defined, and so the derivative of that function at minus 1 can't exist. Now we can also write this as 1 over 1 plus 2x squared for x not equal to minus 1. So let's think about what's happening at minus 1 here. Here's the graph of our function. It turns out that the limit as x approaches minus 1 from the left is positive pi over 2, since the limit as x approaches minus 1 from the left of the inside function x over 1 plus x equals plus infinity. The limit as x approaches minus 1 from the right of this function equals minus pi over 2, since the limit as x approaches minus 1 from the right of the inside function x over 1 plus x equals minus infinity. So what we're seeing is a jump discontinuity at minus 1, but the derivative of the function has a limit as x approaches minus 1. It's easy to see that that limit is 1 over 1 minus 2 plus 2, or 1. So what's happening is that the slope approaches 1 as x approaches minus 1 from either side. So in a sense we have these parallel tangents to the two pieces of the curve at x equals minus 1.